We're going to start in the same place about where we were before, using even the same data file. If you're standing in the ezRA base directory, as I'm suggesting, and in the demo1 directory inside that, this is the syntax. Under Windows, it's spelled py for Python. In Linux, it's spelled Python 3. In Windows, we use backslashes. And in Linux, we use forward slashes. In Windows, we run Python, and we go up one directory and down one directory into the ezRA directory and find the ezCon, short for CON, short for condense. The ezCon program, it's a Python program, so it ends in .py. We feed it a data file, which is in a data directory below us. The N0RQV-8 is the name of the 8-foot dish in my backyard. The 23 is the last two digits of the year, 2023. 02 for February, 09 for the day, and then underscore and the hour, 00 for the 0 hour of coordinated universal time, .text. Let's run that command, and we can see the data files. We've seen it before. It's kind of faint. We see some yellow splotch here, some yellow splotch here, some curtains going along. There's a stripe down the middle, and there's something of a sinusoidal shape across the middle of the screen. I claim that's galactic hydrogen. After some processing of comparing hydrogen to non-hydrogen frequencies, doing some dividing, we can see it more clearly in this graph. Okay, but this video is all about interference, so let's mess it up. How do we remove a sample that's damaged by interference? So with some advanced commands from ezFix that I'm not going to go into, I created a data file with interference on one antenna sample. I called that data file the same thing, but with a C on the end of it, .txt. Just like before, we run Python, we run the ezCon program, and in the data directory, we go get that data file that has the C on it. It looks like this. Where did all the yellow stuff go? We got this bright signal that's taken over, and because of auto scaling, it is now the strongest signal shown on the color bar way up here at the top. And all the other colors are so low down here that we can't see their distinguishing marks. It's like looking at a very faint object behind a very bright object. The interference is getting in the way. If we process a little bit more, we get the maximum signals. For every vertical line sample, what is the brightest frequency bin value? What is the strongest frequency bin value? We put a green dot on it. And then on the brightest of all the green dots, we put a yellow dot. So this is our interference, and that's definitely the strongest signal. But it's only on one sample, one vertical line. We'll see this again and again. It has 908 samples. That's from sample 0 all the way through sample 907. We'll see this change as we take out samples and stuff along the way. Because we compare hydrogen frequencies here in the middle to non-hydrogen frequencies on the lower part and on the upper part, we can simply trim off some of these troublesome frequencies and make them go away. That's what's going on here with AntXT, the T for trimming these high and low frequencies and making them the value 1. Our interference was out here in those non-hydrogen frequencies and was simply trimmed away. We get to see something now. But we can do better than that. What could we do? How about if we just start here and go for the rest of the file? We can use part of the file. We can rescue part of the file just by throwing away the first part. Where do we begin? I suggest just using some other window and as a straight vertical line and figuring out kind of where it lines up down here. If we start at the edge of the window here, that kind of lines up with this tick mark, which apparently represents sample 198, or just about 200, to round it to a nice number. So let's start at sample 200 and plot the rest. How do we do that? Let's go look at the help screen. Run the program, ezCon again. You can have a data file in here or not, I don't care, but put in a -H or even none of this stuff over here, and it will give you a help screen. Try to give you some clue on the syntax. Here we are. It has a bunch of information all along here, but there's a section down here for ANT filters, antenna filters, signal from the air through the antenna, and for the samples which are reference samples. ANTs along in here and ref down here. The first one we're going to look at is what samples to use. Let's start at a certain sample and go to the next number sample. ezCon ANT, so we're dealing with ANT samples, and then which samples to use. Sample use. It has an L indicating I want a list of values after this argument keyword. Here we go. Let's use the ANT samples from numbers 200 and up. We run Python, we go get ezCon, we go get the data file, and here comes the arguments out here. Antenna, samples, and which ones to use in a list, starting with 200 and going up to just a really big number that we're not going to reach. The rest of the file. Here is ezRA, and that's before any filtering, so we see it just as we did before. The next plot is antenna after the filtering, and it certainly has changed color from the purple we just saw. That's good. I kind of see a blob here. I kind of see a blob here. Let's process it a little further. Oh, that makes it much clearer. Somehow we started the plot right here, and the rest of it continued, but there's a section that was missing here. The rest of that sinusoidal shape is missing because we started late, started this far into the data file and only viewed the rest of it. Okay, so that's one way to save some of the data file. Another method here on the help screen, sample snip here and give it a number, something to do with antenna samples and a certain sample, and snip it or remove it or ignore it from discussion. But how do we find this number? We can all agree that ezCon provides a lot of plots. It also provides another file. For every data file out here, we see a file created that has ezCon study on the front of it. It's filled with lots of numbers and text. We look at the first section having to do with the average for each antenna sample's values, and look at the highest values of that signal. It says the highest value was at sample number 183. If we call that 100%, the next highest sample was way down at 13 or 12%. So the first one is much higher than the next. So much so that it even puts a little flag out here to kind of give you a warning. The program presumes so much that it takes this number 183, writes it down here, and pokes you. It says, well, hey, bud, maybe try some arguments like EasyCon ant sample snip 183. Snip out that 183. Just ignore it. I take the hint. Let's snip out that one sample. We run Python, we get EasyCon, we get the data file, all like before. Now we put the arguments EasyCon ant sample snip and the magic number that we saw in the file, 183. This is what it looks like before the filtering, just like before. After filtering, it looks pretty good. I see a vague yellow here and a vague yellow here. After processing, that looks pretty good. It's as if it's just gone away. What we find also, though, is it has one less sample. Used to say 907 down here for the number of the last sample. Now it says 906, because out here someplace there's a sample missing. But we have so many samples to work with, it's hard to see where it was. Okay, for the next demonstration, I want to put it back the way it was. We improved it by removing that sample snip using this command here and 183. When it did that, it created a whole bunch of plots, but it also created an ezB file. EZ, because everything has to be easy, and then B, because it's the second letter of the alphabet. And that's a condensed data file. It's supposed to grind all that information down into a smaller file. It has the name of the same, just like the data file above, but with .ezb on the end. This is an improved ezb after the command. I want to undo that. I want to unrepair that with the earlier command that we used. So we run this guy, and then we actually run a new command running ezplot, a new program. Again, Python, up one directory, into the ezRA directory, find the ezRA ezplot.py program, and it chews on a data file, but it's a condensed data file, the .ezb, spelled differently only on the end. Okay, something different. Suddenly, you are in charge of selecting the basketball team. Here are the high school boys that showed up at your office in the order that they showed up. That's great. Let's do this more scientifically. Who would you pick first for your basketball team? You could line them all up in a row, so according to their height, from shortest to tallest. So what you're doing is sorting their height value, and making it increase always to the right. We'll use that. You might choose the fellow on the right for your basketball team, but if you were selecting folks for a submarine, you might not choose the fellow on the right, or perhaps not for a jet fighter pilot, or perhaps not for an astronaut. Different roles. Here's our data file that we saw unfiltered. If we look at the data for each vertical sample, the average value of each one of those vertical samples, as we've done before, it looks like this. It goes bouncing along at a nice low value, and then pow, that came through with the interference for one sample, and then goes bouncing along and wobbles along. That's nice. Those are all the values, but if we put them in increasing order, so the lowest value first all the way to the highest value, they take this shape. This is one of the ezplot files. It starts at a low value, increases always upwards to the right, and then wow, that last sample was huge. It looks kind of thin, so it's probably just one sample. I want to remove that one sample on the end. Turns out there's a way to do that. Back to the help screen, EZCon, something to do with ants, the antenna signal. Oh, I'm sorry, antenna average signal. And snipping a quantity from maybe the low and the high side of that last plot. So we're removing the lowest, perhaps, maybe 3, or in the highest, perhaps maybe 5 in this example. For our detail, we want to ignore one antenna sample, just the one with the highest value. So we run Python, we run ezCon, we run the same data file as always, and we put this argument keyword in here, snip quantity, and it's a list, so we got to provide at least 2 numbers, 2 things on the end. I don't want to remove any from the lowest values. I want to remove one of the highest values, the highest value. And it looks much better. After all the processing, I don't see the spike in here anymore. That's great. And what we find is down here, we've moved from 907 to 906 for the value of the last sample number, meaning one of these samples is gone. This is much like the previous example, but we didn't have to know precisely which sample was the troublesome one. We just said, take the highest and make it go away. We want to ignore it. If we look at all those samples, values of ant average, sorted in order, it now looks like this. It increases, it starts low, increases always upwards to the right, and it's simply missing that huge spike on the right. After all those samples, that's what it looks like. We saw 906 on the previous page, but it also had a sample 0, so that's 907 samples after all the filtering. Folks that play with statistics look at this graph differently. All this same information is described also in a histogram. A histogram is defined as the value increasing across the x-axis at the bottom, increasing to the right. And for each small range of those values, how many were in there? It was like different buckets. How many values were close to this bucket? What we find is all the values are very well grouped together, except for one that's way over here, that huge spike we had. It had a much higher value. Once we remove that spike, the other ones, the histogram now looks like this of all the filtered data. With auto scaling, it kind of spread out, and we just don't have that large spike over here on the right, confusing things. Well, we use the command up here in blue for antennas. There's also a command just like it, but for reference signals, samples, I should say. I had an example where I needed both of them. We were playing with one from a sample, a data file from February 9th, but this is 4 days later on February 13th. It was unusual. It went along here, and then suddenly there was a spike on the antenna samples. Interestingly, on the reference samples, there was also a spike. Somehow it was way down here. But it really did mess up the data files. Put spikes everywhere. We can understand an antenna spike causing a trouble over here. How is it that a low number creates a great big spike? In all the math for this computation, at one point we compare antenna to reference. we take the antenna values and divide them by the reference. Any antenna value divided by a very small reference provides a very large quotient from that division. So we get a large number showing up in our computed signal. So a low reference can provide a large calculated value later on. In any case, I don't like either of these spikes. How do we get rid of them? They show up in all the data formats. Here's the spike in the antenna, and it calculates through all these different signal progressions. Shows up in ANT B. We got a bump, but we got this big spike in the way. Interestingly, ANT B does not use the reference signal, so there's nothing showing up over here. But here's the reference samples with a spike, and it shows up in all the later calculations. And that's true over here for the ANT spike as well. There is a bump in all these still remaining, but it's got these spikes in the way. How do we get rid of those? If we take all the antenna samples and put them in increasing order, always up and to the right, we see something just like before with a spike right here at the end. For the reference samples, it's the same thing, except kind of on the other side. There's a very low value to begin with to start our sorted list. A low value, and then increasing always up and to the right. The histograms look like this. Just like before, all the samples for the antenna are kind of gathered together with one spike way over here with a high value. The reference is almost the mirror of that. All the values up here for reference are collected together with a spike way down here at a much lower value. So let's use those two argument keywords in a longer command. We run Python, we gather ezCon, we get the same data files before. This line is so long I continue it. This is this one we used already with antenna samples. And here's the same thing, but for reference samples. We're going to remove not the lowest from the antenna, only the highest one by quantity. And on the reference, we want to remove the lowest value, but not the highest value. And it seemed to have worked. Here's the antenna signal with a spike before the filtering, and after the filtering, I don't see it. Over here on the ref, we see the spike before filtering, and after filtering, it's gone. That's because we've ignored two samples. And so now the last sample number is not 905, but two samples less, 903. The last two examples have been using ezCon ant average SNP of a quantity with a list of two numbers following it. There's another alternative, which is not providing the exact number of extreme low values and high values to ignore, but how about expressing that as a fraction or a percentage of the total number of ant average values in that sorted list? Instead of ezCon ant average SNP quantity, how about ezCon ant average SNP fraction? And it's an L, so two values follow. In this example, 0.02, meaning 2%, of the lowest values will be ignored, snipped, and 0.03 of the highest values will be ignored. Instead of an exact quantity, we're now dealing with some kind of percentage. And that may be handy if you just don't know. You may want to just trim off the top 1% or 2% and not worry about it. Maybe come back and improve that later. Many options. Of course, if there's an ANT version, I've tried to make a reference version down here as well. Same syntax, just working on a different set of samples. No example for this one. I'll let you explore that on your own. We've been studying interference by sample numbers. So that's more like a vertical line. Horizontal lines would be interference by frequency. So I created an example. It has a funny name on the end, but it's the same February 9 data file that's been modified a couple of times with ezFix. We take the Python, we get the ezCon program, and we get the new data file, however it's spelled, to display it. And it looks like this. We got one frequency bin that comes and goes, but it's very bright. This is actually a little bit bigger than it's shown, but that's so you can see it on your displays. The calculations will be with one frequency bin. It makes a mess of the data. Holy cow, look at all these square waves and stuff in here. There is a kind of a bump in the right places, but it sure is confused. There is one particular frequency. Here's the 0 mark. These are the low frequencies. So yeah, it's kind of a low frequency over here and in one place repeatedly. How do we find out which frequency bin that is? If we look at the printout as the data goes flying by, we can see just before we print out this plot that we're just looking at, ezCon 317, there's a bunch of data in here for antenna by frequency bin, and what is the maximum value of all those. So that's kind of studying the horizontal line on that plot. The frequency bin with the highest value is 56, says the program. If that was a value of 100%, the next highest would be around 45%. So that's quite a spike. It takes that number 56, assumes it and puts it in here down for you to copy, and pokes you and says, maybe you should try an argument like ezCon working on the raw samples. That's the antenna and the reference samples before they got divided. Frequency bin, and hide something. Hide a frequency bin, number 56. Sure enough, I run the program for every raw sample, copy frequency bin 55 onto its neighbor frequency bin 56, the troublesome one, to hide it. We run Python, we run ezCon, we run the data file, however it's spelled. And here's the argument out here that we talked about, hiding frequency bin 56. And it cleans up the data very nicely. Cleans it up so much we don't even see it in ANT raw. The filtering's done way up here before all these, up in the raw samples. And it seems to have gone. We see the bumps where they should be. It has the same number of samples as before. We simply copied onto one frequency bin's set of numbers for every sample all the way across horizontally. So nothing was removed. It was just tweaked a little bit. It was covered. It was like putting wallpaper on top of it. It was hidden. The plots came out nicely. That's good. None of that up-down square wave problem. And that graph came from this one. One of those frequency bins is copied, but I can't figure out which one it is. I can't say. Actually, it has to be way down here anyway, which was trimmed off. And then I made it worse. I added interference on 2 more frequency bins, and they weren't on all antenna samples. Those could be easily ignored, but they come and they go. So to see that, here's the data file I created. We run Python, we run ezCon, and we run a data file. This has a remarkable spelling now. However it's spelled, we put it in. And here it is. We now have 3 frequency bins with trouble on them, and they aren't even at the same times. They come and go at different times. And it makes a mess out of the data. Wobbles up and down. Down here, we can see all kinds of different levels going on. What trouble. When we look at the frequency response, for each frequency bin, what is the maximum value it saw? Wow, okay, 3 big frequency spikes. We know how to get rid of frequency spikes, but what are their frequency bins? Which ones to remove? We look in the same place in the printout of the program. It flies by as it starts to print out ezCon 317 plot. But now we see 3 of them. It's got a 100%, a 97%, a 94%, until it drops way down to 45, where it probably levels out. Because of that big drop, you get a flag out here. And the frequency bins are 56, 206, and 106. Let's just run that same command structure, but with 3 different times. We run the program, we go get ezCon, here's the data file, however it's spelled. Continuing the line, ezCon raw frequency bin, we're going to hide frequency bin 56. Same thing, but frequency bin 106. Same thing, but frequency 206, all on one line. I suggest increasing order of those numbers, just in case they happen to be consecutive numbers. If the frequency bins are right next to each other, it's best to do them in increasing order. And that cleaned up the spectrum a whole lot. The 3 large spikes are gone. The data looks pretty good. It doesn't even show up in the ANT raw because it's done way up here before then in the raw samples, before ANT and reference are even identified. We see the bumps where they should be. The sample numbers have not changed. We lost a little bit of information in frequency, but it was pretty corrupted already, as we could see. And yet there's another way to repair samples damaged by interference, particularly if they're just a few frequency bins tall. So I created another data file with interference. This one has interference that is 3 frequency bins, consecutive ones, high, and not on all antenna samples. We know that causes trouble, coming and going. This data file is spelled the same way except EB3 on the end. 3 frequency bins high. So to look at it, just like normal, we run pi, we run ezCon, we run the data file. And we get something that looks like this. It's not 1 frequency bin tall, it's 3 frequency bins tall, and it's some range of samples, but not all of them. It messes up the data something awful with a great big square wave in here. But there's a tool that perhaps can work. Down here in the ant section for antenna, we see ezCon, of course, antenna, something about frequency bin and smoothing. And it takes one value, 1.1 in our case. Well, in the example case there too. It turns out to be the same in ours. So if you consider each antenna sample separately, and think of it as a long hedge, a long set of bushes that need trimming. And the bush is made out of all these different frequency bin values. Some are higher and some are lower. What you want to do is trim that hedge to a nice smooth curve. You want to shorten any frequency bin that's sticking out that is significantly taller than its 4 closest neighbors. 2 higher frequency bins and 2 lower frequency bins. For each antenna sample separately, each frequency bin value should not be greater than 1.1, there's that value, times the average of its 4 frequency bin neighbor values. Okay, a bunch of math, but let the computer do its work. We want to say Python, we run ezCon, we run the data file, however it's spelled. Here's the argument keyword, and we're going to put in a value of 1.1. The raw value, we can see the strange square value on here. But after that, it's kind of cleaned up. I don't see any nasty square waves over here. Hurrah, that looks pretty good. We did not have to know which frequency bins were troubling. In time, we didn't have to know which sample numbers were troubling. We just gave it a parameter and said, clean yourself up. It's a smoothing filter. On the graphs before, it would be going down each vertical line sample and making sure there was no strong signals higher than its neighbors. This worked quite well for 3 frequency bins of a interference pattern. This is the same, but for 4 frequency bins, and it looks pretty good. But if you go higher, like 5 frequency bins, the math starts breaking apart, and the square wave doesn't fully get filtered out. So it's good for some kinds of interference. It's rounding and smoothing and sanding off the sharp corners of the frequency bin response, which is important more for velocity information later on, but perhaps not for intensity information, which is what we usually plot up on the sky maps. Thank you for coming. Hope to see you in the next video.